we are using SI wave. Then for parasitic RLCG extraction, we are using Q3D. Microwave passive circuit analysis, we are using again EMA 3D cable, and for bio implantable devices and any medical applications, we can design in HFSS. So similarly, for high frequency tools, we have HFSS, EMIT, SI wave, EMA 3D cable, EMA 3D charge, or AMC charge, then Q3D circuit, Neuhart, IcePack. In case of low frequency part, we have Q3D circuit, Neuhart's IcePack, Simpler, MotorCAD, and Maxwell. So now I will uh, give brief introduction regarding this HFSS, so you all know about this part. HFSS, in case of HFSS, first, in case of designing of any antenna, first we'll start with theory or background equations, rather say. So once we have the designing part, we will start with the geometric designing using HFSS. We'll apply mesh to it, we apply solvers to it, and then we'll start optimizing design. And once we'll run the simulation, we'll get to know our antenna is operating at our desired frequency or not. If it is not, again we'll do the optimization and we'll try to achieve our operating frequency. So that's how the whole process in HFSS. So in HFSS, we can design antennas, waveguide, filter, PCBs, then integrated circuit packages, connectors, radar equipment, cell phones, EMI, EMC analysis. So we can able to do using these tools. So I have already explained about SIWave. This is mainly used for the PCBs, where finite element method and finite method of movement, these two solver mainly we are using. And its applications are, we can analyze here EMI, EMC, then signal integrity, power integrity, PCB signal integrity calculation, high speed serial channel design, DC current voltage distribution on PCB, like that we can able to do in SI wave. In Q3D extractor, I told it's used for parasitic extraction. So where transmission line, bus bar connector, these are few examples. Specific value of inductance, capacitance, resistance, we can able to find out in Q3D extractor. Then again, this is Ansys EMIT, where this is used for analysis, where EMI, EMC analysis we can able to do with between the transmitter and receiver. You can see it here. Mainly in aerospace application, this is more useful. Then next one is IcePack. So you all know about Arduino Nano or Raspberry Pi board. So these boards, sometimes if you might have also feel when doing some coding or running continuously code in Raspberry Pi, sometimes it will heat a lot. So generally when we are going for fabrication, before that we need to do this heat analysis part, and sometimes it is not properly done, then heating problem we can able to find in many boards. So where this IcePack plays very important role for doing thermal management before fabrication. So all detail analysis we can do in IcePack. Next one is EMC plus. So you can see it here, a bunch of cables are together. So when this kind of scenarios, there is high chance EMI, EMC loss and issues will happen here, so that we can able to rectify using Ansys EMC plus. So these are few examples for Ansys Charge Plus, arcing in HV system. HV, you can see here, HV switches, lightning attachment modeling, solid dielectric breakdown, PCB flashover, and EST gun. So these are the few examples we can see for Ansys Charge. Next is Neuhart filter solution, where again this is used for filter designing only. So these, once we are opening this, if time permits, I'll show how we can able to design this part in Neuhart filter. This is one of the important tool you all have used, I guess, antenna extension, antenna toolkit and ACT extension. where a number of antennas are available. You just have to choose which design you are looking for, write their operating frequency, synthesis the design. You will get the proper whatever design you choose, and you can run the simulation and you can get the output. So here are some simulation performance examples, where first figure is talking about signal and power integrity. Then you can see it here, antenna. When vehicles are moving from one place to another place, how um, the antenna's radiation is happening and how it is its range basically you can able to find out in second picture. Third one is talking about the 3D view of filters. Next one is RF coside in aeroplane. This is very familiar. You all know about the biocompatibility. When any device comes in direct contact with the human body, it should not harmful to human body. So that's why we are considering always biocompatibility. And specific absorption rate is one of the parameter which are we using while designing any antenna. So it should be less than 1.6 watt per kg, and we all are using mobiles, so you might have checked for all mobiles SAR also. So it is generally in between 1 to 1.3 watt per kg. So next is talking about antenna placement. Here car, one car is there and I have kept antenna in the mirror. You can see this is the zoomed part of the mirror. Here FIPA antenna I have placed in the left mirror of the car, and how its radiation pattern gain, all those analysis we can find out in this example. So I have covered this antenna placement part in February. I have done one webinar in that part. So let's talk about 5G technology. So you all know it is smart connectivity, we can say. In 1G we can able to do only voice communication, and 2G we had only voice and text communication. In 3G we have voice, text and internet uh, accessibility, and in 4G we can able to communicate like voice, text, internet and multimedia. In 5G we have smart mobility, smart parking, we can able to do car to car connection, car to car communication, smart wearable. We are already using smart home, smart security. So everything is a little bit advanced compared to the other uh, 1G, 2G, 4G, and 3G. So addressing a complex matrix for this engineering goal, mainly it is depends upon the performance, miniaturization, and time and cost. So before going in deep, I would like to give again a brief intro about this fifth generation where we are doing simulation part in HFSS. So here, smart connected products like requires which have a rapidly increasing the communication bandwidth, but radio frequency spectrum available is growing at a much slower pace. That should be needed. One way in fifth generation, the cellular wireless technology, 5G can address the problems by leveraging the beamforming antenna to send different signals to the different area of cellular network. So enabling the multiple simulation transmission at the same time on the same frequency. So that is the main important part here. In case of 3G and 4G, cellular technology generally preferred the process of dividing frequency bands into even narrower segments and splitting time into smaller and smaller pulses to increase the number of mobile users that can be accommodated by the network. So sometimes if you are observing this, you will get to know when crowd is more, you will get the less signal. So it's because of the signals are getting divided there. That's why that fast communication we can't able to do. So in 5G, we have mainly focusing about this performance, miniaturization, and time and cost. As we know, 5G is its speed is 10 times faster than 4G, and it has ultra low latency, that is less than 1 millisecond. low power, that is less than 5 watt. Also, 5G designing focusing on its miniaturization. Uh, Mainly, these are some standards we are taking in consideration. So, what is this JEDC, JEDEC, then AECQ, ISO, and IEC? I'll tell in brief. Where JEDEC stands for Joint Electronics Device Engineering Council, which is focusing on development of standards for microelectronics engineering, including semiconductors, device, and memory. And this is used for package outline and thermal management purpose. In case of AECQ, it stands for Automatic Electronic Council qualification, and these are specific for automatic industry, and it is used for to ensure the reliability and performance of electronic component used in automotive application. So again, this is used for the aspects which include in this is temperature management, humidity, and mechanical stress testing. In case of ISO, it is International Organization for Standard, and IEC, it stands for International Electrothermal Commission, and these are used for the thermal reliability. ANSYS simulation and assessment involves heat dissipation, thermal management, and temperature dissipation. So if I'm talking about the lifespan, it is more than 10 years. Now, in case of time and cost, by 2025, in context of this 5G, it involves the multi-phases approach, including design, testing, optimization, and deployment. So, to minimize the operating cost and optimization, network energy should be divided into certain parts. So now these are main important factors for while designing this 5G systems. So we have high bitrate systems, end user equipment, edge processor, micro infrastructure, and electrically large communication environment, network modeling of electrically large RF communication environment. So in case of high bitrate system, in telecommunication, bitrate refers to the number of bit transmitted per unit time. In context of 5G, this high bitrate is a key feature that allows the transfer data faster, and also it is useful to improve the network performance. So it has segments like pre-layout design, RFI, EMI, EMC, EST, then optical integrity. In case of high-speed signal integrity, power integrity team, we have power integrity and reliability, signal integrity analysis. In case of design reliability team, thermal integrity and design reliability, these are main important part. In case of end user equipment. Here, by using this ANSYS simulation, engineers can gain insight into behavior to end-to-end equipment in 5G environment, which enables to make decision, optimize the performance, and improve the overall experience. So when it comes to user end equipment, it's a requirement to ensure optimal performance, reliability, and compliance with industry standards. So again, in case of antenna design, there is multiband and milliwave antenna design, antenna system placement integration, 5G statistical analysis, then external effect and human body interaction. Then in case of design reliability team, we have electrothermal reliability and management. In case of system team, we have to do system integrity. Now the edge processing requirements. Edge processor plays a crucial role in 5G technology. It enables a faster data processing and reduces latency by bringing computational capability. So these processors are deployed at edge of network, like near end user device like IoT devices, allowing for quicker decision making and improved overall network performance. So in this edge processing requirement, we have three teams like in front end team, back end team, and packaging team. In front-end team, we have power budgeting. So managing power efficiently is essential to ensure the reliability and sustainability of 5G infrastructure, including the base station, user equipment, and other network components. In case of packaging team, uh, chip aware packaging system validation is playing a very important role where for seamless communication, optimal performance is required, and we need to validate the chip. So its function is the verification and performance testing. In case of this backend team, we have IP and custom validation where package awareness of SOC validation we are doing. So here, um, understanding the packages and awareness design, then EMIC, that analysis we are focusing in this part. In case of IP custom validation, it ensures the standards of IP blockage or custom designing elements when it is specified we are using for particular applications or based upon requirement and functions in case of this 5G. The next one is micro infrastructure and electrically large communication environment. So again, it has the antenna design team, RF system team, RF team, and mechanical and thermal team. In case of antenna design team, base station antenna, array design, micro array installation and integration comes in picture. In case of RF system device, channel modeling and communication analysis we need to do. In case of RF team, we have modeling simulation environment team and then connectivity of this RFI and signals and their analysis we need to do. In case of mechanical and thermal team, multiphysics and electrothermal modeling we need to perform. Large communication in um, RF environment with the network modeling. It has two main important parts, physical layer and network creating. In physical layer, we need to build RF environment, model, dynamic links analysis, and path prediction with urban propagation we need to do. In case of network creation, build network, analyze the network performance of physical layer. So these are the main important part, and the goal of this large communication RF environment is to perform the network in co-simulation with a high fidelity physics based environments of the physical layer. So these are our other products. Like in case of semiconductor, Redox SE is used for the processor design, Redox SE electrothermal used for the chip and IC package design, Power Artist is used for the power saving purpose. Or in case of chip failure analysis, we need to do, we are using Pathfinder tool, and EMIC analysis, we are doing Rafter Edge. In case of embedded suit, we suppose we are doing applications, we are doing work in applications like EV, ADAS, or IoT. Skate suit is one of the important tool in embedded we are using. In case of optical and VR, we have SPEMOS, PIOS, ZMAX, and numerical FTTD, numerical mode, and numerical multiphysics. So this is one of the important slide where suppose anyone wants to design advanced antenna lab, they should have Ansys HFSS, EMIT, IcePack, HFSS 3D layout, and circuit. These are the tools which we required for designing antenna lab. In case of PCB simulation lab, we required HFSS 3D layout, SI-Wave Q3D, extractor, IcePack, etc. So here for other labs also like embedded and embedded systems for lab, we required ANSYS CAD, Medin, then Speos, Twin Builder, SDK, etc. So this is one of the important slide. You can make a screenshot or you can make photo of this. So here are main important learning sources: ANSYS innovation course and ANSYS learning hub. So I multiple times I told you have to create account as ANSYS innovation courses. You can able to access more than 40 courses which are free of cost, and you will get certificate after finishing the course. But once the course, one course will take approximately 2 or 2.5 hours, and you need to write a test over there. Approximately 10 to 15 questions will be there based upon whatever you have learned in that 2 hours. You will get, after passing the test, you will get certificate for that particular course. So these are two courses in electronics part. In ALS, that is Ansys Learning Hub. So here you can see more than 900 recording videos are there, and these are based upon self-paced learning. So based upon your time and requirement, you can start the course and you can finish it as your time availability. So here, more than 45 plus topics specific in learning room is available. Also, we have 200 plus centers, live classrooms also available, virtual classes also available, and more than 250 plus courses you can find out, and 1000 plus workshop available in ALH. So here you can see this is the ANSYS campus where electromagnetics is one of the part in that. So you need to click on that and you can able to access the electromagnetic part. So again, here are some other platforms also, like structures, fluids, systems, photonics, etc. So this was the brief detail about the 5G part. Now we'll move towards the designing part. I'll first design antenna for 38 uh, gigahertz, and then I'll move towards antenna for 28 megahertz, and some array also I'll show. So let's start with the 5G antenna designing. We'll see its array part also, and then we'll move towards the antenna for 28 gigahertz. So you all know in 5G we have 5G network frequency. Uh, it is more than 6 gigahertz, and then again mmwave band will come in between uh, 25 to 28 gigahertz. So again, that's why I will cover 28 gigahertz part also. So let's design the antenna which is working for 38 gigahertz. I will be little fast. I want to cover one more design so that we can see here two types of antenna. So first, uh, I will draw the substrate. I will create a box and assign this as a substrate. I'm using here FR4 substrate. I hope you are previously, I hope many of you used HFSS previously. So I'm not going to uh, going in deep how to start a project or how to create uh, boxes where you'll find out all those things. So I got this box from draw. I went to this box and created one box here. So I have to now change its material, and I will give dimensions for that so that my substrate will get created. So in this, just double click on box one, you will get this window where you can choose the substrate. Here you can see many substrates are available. So based upon your requirement and its relative permittivity, loss and tangent, those analysis you have to do before and choose material accordingly. Just so I'm changing its color also. So I'm first putting the parameters which I'm going to use here. I will add variables which I'm going to use in this. So I here go to project variable and go to add. So here we can add uh, the variables or parameters you can say. The first length and width of the substrate is represented by LS and WS. So LS is length of the substrate and its unit is mm. The length is 6.2 mm. Then width represented by WS. Unit type is length. Its value I'm assigning here 7.5, 7.4. So next is height of the ground, which I'm going to represent by HP. And again, it's in all the uh, dimensions are in millimeter. 0.035, the height of the copper part is 0.035. Then height of the substrate is represented by HS. Then length in unit mm. I'm assigning as a 1.1. Then A is one of the variable which I required for patch designing part. So I'm assigning A as 0.8 and WP is a again uh, the length and width of patch also we need to put it here. So WP is the width of the patch and its value is 2.5. LP is of length of the patch 3.5 and width of the feed line represented by WF. And again, its value is 0.75. So let's finish this part, apply, and okay. So now I already first we'll create a ground plane. So this is our box one. I'm giving this box one name as a ground. On the top will be one substrate and on substrate we'll create a patch. So just ground and I'm assigning this with the copper because just imagine we have substrate far four on the top and bottom we have copper part. So bottom part I'm considering as a ground. So it is a full plain ground I'll say. So I'm assigning the material for that copper and name is ground. I'm selecting the color orange because almost copper will look like this color. I'm assigning the dimensions for that now. Now its positions are this 0, 0, 0. X size is dollar LS, which is 6.2. Y size is WS and Z size is 0 HP 0.035. So you can see it here, all the values and just say apply and okay. Just control D. Our ground plane is ready. Now on the top of that, we need to create one more box, and that will be our substrate. So just create one more box and create a substrate. Rename is I'm renaming this box one as substrate, and its material is FR for epoxy. So I'm changing the color also. Like, okay. So now we have two layers. This is our ground plane and this is our substrate. Now we are creating the third layer, which will be patch, because now we have a ground and substrate with us. Third layer will be patch. Again, create a box. Sorry, not rectangle. I need to create a box. Draw. We are creating now patch. This is the box 3, and I'm renaming this as a patch. This antenna will operate for 38 gigahertz. You can see the length and width of the antenna is very small, 6.2 mm by 7.4 mm. We create a material for this is a copper. Okay. So its dimensions are, its position is, first we'll write a comma minus ws by 2 minus wp by 2. hp plus hs. So its position is 0.8 mm, comma minus 4.95, comma 1.135. Size is LP, that is 3.5. Y size is WP, is 2.5. And height of the substrate 0.035, which is again HP. So you can see it here, 3.5, 2.5, 0.035. Just apply and OK. Now this is the patch. You can see. Now we are creating the feed. I'll create one more box, and create a feed. So this is, I'm renaming as a feed. Upper I required apply and OK. Now give the dimensions. dollar $A plus dollar $LP dollar WS by T minus dollar WF by T HP plus HF is size represented by LS minus A minus dollar $LP. So it's 1.9 and Y size is root of the peak, that is WF. Therefore, is the height of the cotton, sorry, copper. 375 HP. Just apply and see. So it got created. You count. By mistakenly, I changed the dimensions of substrate. So once again I need to put in the feed. Position is $A plus $LP, comma $WS by 2 WF by 2 and HP plus HS. Exercises dollar LS minus A minus LP So this is our feed. This is our ground. This is our patch. Substrate dimensions. I need to change because unknowingly I have done this 0, comma 0, comma. It is at height HP. So position should be 0, 0, 0.035. X size is ls, $ls. Y size is $ws. And height is 1.1. That is HS. Yes, it's done. This is our substrate also ready. Now we have to create a, we need to excite the port. For that, we need to create a rectangle over here. Before that, I will just add copper part together. Just this patch and feed and go to modular boolean unite. Patch is ready. Antenna miniaturization also will play a very important role. That's why you can go for higher substrate, higher dielectric substrate, or you can modify ground. You can modify the patch by adding slots or mindered line, or you can use metamaterial or magnetic dielectric material. There are so many techniques. You will once you will see the review papers on that, you will understand. Now we are changing the plane and creating a rectangle over here, and we'll excite the port. So let's change the plane. Once again, this is port. This is the position of our port. The Y side is WF, and Z side is minus 1.135. It is apply. Okay. Now we'll excite the port. Just right click over here. Sign excitation port. Lumped port. With the register impedance and considering new line. Just zoom it and create it. line over there. Just click and create. It's not defined. Just zoom it. Yeah, it's defined now. Just next. Finish. Go to analysis. Right. Give now operating frequency. You can see it here excitation. This is our excitation now. And we'll give the solution setup for this. Right click add solution setup advanced. Operating frequency 38 gigahertz. Number of passes you can keep 6000 as 18. And this range I'm giving 18, 19 to 57 gigahertz. I'll just reduce the number of points so that simulation will finish fast. And click on OK. And boundary conditions. Create a condition 38 is a radiation box. So when you are using rectangle, in that case, separate, you need to add a boundary condition. In case of, if you're putting as a three-dimensional box, no need to give a separate boundary condition PEC to it. You'll consider as the bound metal only. So let's just do the validation check. So it's correct. Now we'll simulate it. And saving and now in case of array using domain decomposition method, as we know, array that finite array wizard assume that each element in the array is physically same with the same field pattern. Array and also in case of array uniformly excited in magnitude. In case of HFSS, we can give here phase shift. That unit cell needs to have a coupled boundary conditions that I'll explain in once the simulation will get over. We'll see these results and we will move the array design using domain decomposition method. So when we are creating a box around that, there will be some boundary conditions over it on the primary and secondary surfaces. Then coupled boundary that forces periodically in field that will help us to um, generate the first and secondary boundary over there. We'll wait for 5 minutes and then once the result is getting generated, we'll start with the domain decomposition part. Before that, I would like to show I'll see any ready-made result is available with me so that I can process first. So yes, after simulation, this is the design where we have done right now. So what resonance we are getting after completion of the simulation? This is the S parameter, you can say. You can see it here, which is operating at exactly 39.15 gigahertz. Then if I'm putting horizontally one line at minus 10 dB, you will get bandwidth for this antenna. So M2 and M3, these are the 2 points where we can able to find out the bandwidth. So it is for F1 is 37.70 gigahertz, F2, F1 is 37.70 gigahertz, F2 is 40.89 gigahertz. So approximately 3 gigahertz, that wide bandwidth we can get in this antenna. And compared to that, the size is very, very small, 6.2 mm by 7.4, and height of the substrate is 1.9. Now let's see the gain of the antenna. So this antenna gain is 5, 3.5, 3.4. You can see this is the popular map gain. This is cross polarity. We'll see field overlay for this. Radiation field. Game plot. We'll see approximate transient and apply and close. Just go back to the design. Yes, you can see this is the gain plot for this antenna. Now we'll see the array part. So what I'll do, I'll save this design and I'll create a array. Um, See the gain. We got to create path is plus gain. So this is the gain. I'm just copying the design and pasting in the same project. Control copy and paste it over here. And I'm renaming this as a array. So when we're starting designing array, change the solution type HFSS with a grid array. First thing you need to do is remove the boundary conditions open region boundary condition it has no that first step is to remove that delete. I just have I deleted the boundary condition. Next this is the air box we have. Now this select whole body. Then we need to assign boundary conditions, right? So just right here for or here boundary coupled auto identity auto identify lattice pair. Just click on okay. So you can see it here two boundaries got created. Lattice pair 1, lattice pair 2. So this angle phase delay will help you when you are performing the beam forming. So I'm not going in that. I'm just showing you how to create these angles. So go to this lattice pair 1 phase delay. You can create here phase angles. So I'm giving name as a phi scan and theta scan. And I'm keeping at 0 degree only. I'm not going to change its angle here. But how to change that? You can use this variable. I'm assigning angles as 0 only. Then once you're done with the lattice pair 1, automatically same things will get created for lattice pair 2 also. See, before I just created for lattice pair 1, but lattice pair for 2 also automatically theta and phi angle got generated. Now we have boundaries on the sides we need to create for top and bottom. So for that, we need to create a top and bottom surface. Surface 1 and surface 2. Simultaneously, we need to select those two and right click. Okay. I hope bottom also got selected now. Yes. Percent boundary, radiation, and done. Now we need to create an array. Let's go to HFSS. Uh, Go to model, create array, and here I'll create two by two array. Two, its size is 2 by 2. Padding cell is 1, and click on OK. You can see here array got created here. Go to active cell, and you can see the active cell is available 1 by 1, and this is a total overall 2 by 2 cross section array. Just click on apply and just close it. Now we need to give the values for radiation. Go to radiation, right click over here, insert far field, because we need to do far field setting for 2D and 3D. Just go to uh, infinite sphere, rename as a 3D. Start with -80 to +180. Theta is again -180 to +180. Click on OK. Now we'll create the azimuth plane and elevation plane. Similarly, again do the same thing. Insert far field, infinite sphere. Name this as a azimuth plane. So it's -180 to 180, and at theta it is 90. Just click on OK. Now elevation. Elevation. I'm keeping the starting with 0. Start with 90. Let's take care also 90. Starting theta is at starting with -180 to +180. Steps as we done. Now we'll see the solution setup. Go to analysis. It should operating frequency it is same only, everything I'm keeping same. So I'm saving this field. Click on OK. Then see the analysis. Validate checking will do. And run the simulation. This is the 2 by 2 array. The remaining two designs I'll show its result first, and then I'll move toward the antenna operating on 28 kilohertz. I'll show its results. This is the 2 by 2 array for 5G antenna. You can see its results. So this is the S parameter after running the simulation, which is operating at 39.1950. When we are doing array, it will affect its gain actually. So you can see the realized gain. It is 3.9. Before in single element array, it is 2.07. With 2.2 by 2 array, it is 3.37, 3.97. So that's the main part in this array. The overlay. You can see this is the field overlay for 2 by 2 array. Now we will move towards the next design part, analysis of phase array antenna for 5G applications. So So in this actually three parts are there to design first single element antenna using HFSS tool. So this is the coaxial field antenna I have designed. So how to design that quickly I will tell. And after that I have created the unit cell for this. So this is the unit cell. At the bottom you can see it here, antenna is there. Yes, this is the antenna at this bottom. And I have created the boundary conditions over there. You can see it here. Uh, this is the master 1, master 2, slave 1, slave 2, and this is the antenna. The next step is to create the array, and that I have created here. This is the array, control D. You can see here 4 by 4 type of array I have created using the same method which I have shown to you. For that, we are working with 38 gigahertz, but for this design, we are working with 28 gigahertz. So I'll just fast tell how I have done that with a simple design. I'm creating a new project here. The design part of this single element from HFSS toolkit, how we can do. Just directly go to antenna. Creating a patch antenna, which is rectangle. It's a coaxial rectangle probe coaxial tube. So here it is operating at 28, but I'm changing its dimensions also. It's not exactly what after calculation synthesizing here I'm getting. I'm not using the same. I'm going to change those things. It is operating at 28 gigahertz. I'm using substrate as a diuride. Height of the substrate I'm keeping 0.157. Here it is 0.175. I want to change it by First, let it synthesize and then we'll change the dimensions. Mm, Finish. I'm going to change the dimensions for this. Go to project manager, select the design. You can see it here. I'm changing its dimensions. I want length, patch dimensions by 40.42 will be length of the patch and width is 0.31, 0.31. It will change accordingly there. I want height of the substrate 0.07, 0.078. That is 10, 0. This is nothing but 3 into 10 raised to 8 C by F, which is nothing but 3 into 10 raised to 8 by 28 gigahertz into 0.44. So I have to do calculation. Its values are after calculation 0.4714 to 857. You can see this is the feed width. 0.0508 like this. 0.172 like this. And eight. So this is the coaxial feed antenna is ready. Here, select its ground and patch. Right click, assign boundary, finite conductivity. Then select here this use variable and click on vacuum. So here select copper. And click on OK. Click on OK. Just go to the boundaries. You can see it here. Two extra boundaries got created. Just remove. This will remove the extra one. Antenna, neutral, delete. This is antenna ground. Now we'll see the solution setup. What I have done, I just removed this. Before it is the auto open region was there. I just unclicked on that. You can understand. After doing that, automatically the radiation box got created over here. You can see before only two boundary conditions were there. Antenna ground metal and coax outer. After doing that setting, this auto open region also got created. So we'll validate the design and see the result. Yeah, solid. I'm keeping Z uh, padding to 0. When you get to Z padding, I'm keeping as a 0. Control C and send the simulation. This antenna, the simulation will take a lot of time. I will show direct results to you. So this is the same design. I'll show you the return loss. I think I need to run the simulation. Yeah, I have the uh, results for this. This is the same design. Let's see the return loss. So this is the return loss, which is exactly at No, but it is not that good antenna. Minus 10 dB it is. I think I need to wait for this design, which currently I have did the analysis, that there I can get a correct, accurate result. But already explained you the steps, like one we have done with the coaxial cable, and for 38 gigahertz antenna we have simple microstrip patch antenna we have designed, and we perform the phase domain decomposition method for array design. So the same way for this 28 gigahertz also, once the coaxial cable is getting at exactly 28 gigahertz, the same process we need to follow and create a uh, array like this. So that's how we can enhance the gain of the antennas. I think this simulation will take time. Generally, when array is there, no, it will take a lot of time. That's why I try to do it again, but I don't know why the results are not available here. I ran this before, but I think I did some modification in the design. That's why the return loss, this value is not available. I need to perform the once again validation check. Yeah, it's good in all possible steps, and then I need to run the simulation. I hope this session was helpful to all of you how to design the 5G antennas and create array using domain decomposition method. This is our uh, coaxial cable antenna, and in case of unit cell, this is the master. First of all, creating boundary conditions, you have to creating this unit cell first. We need to change in this uh, padding or of X padding, Y padding, Z padding in positive direction. I'm keeping X padding is 0, Y padding is 0, minus Y padding also 0, minus X padding also 0. Only I'm keeping positive Z padding, which is 1.071. Otherwise, other remaining padding I have removed. So that's why you can see it here. Antenna is at the ground part, and uh, only towards the Z axis. Some at some height you can see the unit cell, and boundary conditions you can see it here. This is master 1, this is master 2, slave 1, and slave 2, and this is the antenna ground metal. So along the, you can see this is a view where our ground is at exactly at the middle, antenna is exactly at the middle towards the Z direction. You can see XYZ direction, you can see. Along the y-axis, I have created master 1 and master 2, sorry, master 1 and slave 1. And along the y-axis, yes, along the y-axis, I have again master 2 and slave. Yes, so this is the return loss. I need to do optimization because uh, resonance is at 28 gigahertz but minus 10 dB return loss only. So results will not be that accurate. With this minus 28 gigahertz with minus 10 dB return loss, the gain is 6.94. So you can see it here. This is for when unit cell is there, no? This unit cell, after applying boundary conditions to it, you can see return loss because we have given uh, ports like lookup port and it, it's coming like in this way where I used this one where theta and theta scan is 90 degree and phi scan is theta scan is sorry phi scan is 90 degree and theta scan is 60 degree. So that time I got this resonance where its uh, frequency is 28.47 gigahertz with minus 27.74 dB return loss. So similarly, you can see this is one more uh, theta and phi angle where you can see phi scan is 0, theta scan is 60. So in that case, antenna is operating at, I'll show that also mark by putting marker. It is operating at 26.97. So that beamforming I told no. So when I'm keeping theta and phi value 60 degree and 90 degree and 60 degree respectively, where I got exact at 28 gigahertz result. So I'll show the gain with this is with phi 90 degree 90 cut and phi 0 degree. This is phi 0. This is the realized gain. You can see is 14.36. So we'll see the field overlay. If it is possible in this case, then you can understand. We see for gain, realized gain 1. Okay, close. You can see it here, gain. I hope you all can see this. This is our antenna and this is the gain. I kept field overlay so that actually half part is due to this box you can't see, but you can imagine this is at the bottom side and this here at the top side. So this is the realized gain. In case of array also we will see the result directly. This is the array 4 by 4 array. Now I have to run this also, then only we can see it. But it's the same process only, what I have explained for 38 gigahertz. Apart from that, I already explained everything, how to see this This change also. Any doubt is there? Good evening, ma'am. Design parameter calculation. Which design, ma'am? How to design this 38 gigahertz and 28 gigahertz? These are very basic calculations you will get to know in research papers. So that's why in deep I never went. I just took the calculations on that design and I started plotting the geometry. So that you can find out in any research paper. Coaxial cable design and simple microstrip pattern design. Any other doubt is there, then you can write in chat box or just unmute yourself and you can talk. Apart from that, I have covered all the part. Only one part is pending for this 28 gigahertz array antenna. Still, it is running. If it is running within 5 minutes more, I'll show you. Otherwise, we'll end the session here. ADT we can't share, ma'am. We can't share our design to you. Recording you can share. You can see. Yes, design is ready. Simulation is completed. Mm, let's see the output. This is the gain. Gain is for 4 by 4 array. It is 15.18 dBi. You can see it here. This is the gain. This is a 2D gain for 28 gigahertz. You can see it here. When phi is equal to 0, you will get this red shape. When phi is equal to 90, you will get this brown color shape. So this is the output for this design, which is working on 28 gigahertz. We'll see the rating frequency also. Return noise. Total 16 arrays are there. That's why maybe this issue is happening. But yes, this antenna is working with 28 gigahertz. And this is the gain. I hope you understood and the session would be helpful for you to designing 5G antennas. Thank you so much for joining us.